This video is about projectiles. All right, so fun. Whee! And let's not forget our key to projectile problems. Definitely keep them separated. And we need to remember about vectors and components. So just a quick little review about vectors and components. If I have a vector that's going off at an angle, and I make that a velocity vector, I can split that vector up into two pieces, one that's going this way and one that's going that way. Maybe I could call that one Vx, and maybe I could call that one Vy. So that's just something important to remember that we'll be able to do. So let's start off with an example problem. So let's say that the walrus comes along and kicks this ball from ground level. We're going to stick with problems from ground level right now, and gives the ball an initial velocity, and we'll make things really easy to start off. We'll say that the initial velocity is 40 root 2 meters per second, and there's the ball. And then let's keep this angle as 45 degrees. And what I want to be able to do is figure out the range. That is, how far away does the ball land from its starting position. So what do we do here? Well, in the theme of keep them separated, the first thing we need to do is we need to take this 40 root 2 and we need to split it up into components. So we're going to say one piece of that 40 root 2 is going this way, one piece is going that way. And because I chose 45 degrees and 40 root 2, that means I can very easily write this as 40 meters per second. And I didn't leave myself a lot of space there. And I can write the horizontal component as 40 meters per second. Maybe I'll write this V0 in the y direction, and I'll make this V0 in the x direction. So, and then this one over here, we'll just call this one V0. Once I've split things up into components, I actually don't really care about my V0 anymore. This thing is not so useful to me. What I care about is the initial velocity in the vertical direction and the initial velocity in the horizontal direction. From the vertical direction, we're going to find the total time in the air. How are we going to do that? Well, we're given a problem now. Let's forget about everything else that's going on because we're going to keep things separated. We're just going to look at the vertical direction. So in the vertical direction, I've got a ball that's being launched up with an initial speed of 40 meters per second. And I want to find the total time in the air. I know that gravity is going to take away 10 meters per second every second from this 40 on the way up. So it's going to go 40, 30, 20, 10, 0. 4 seconds to go up, 4 seconds to go down. So that's a total time of 8 seconds. Right? If you are an equations person, then you can do acceleration is change in velocity over time. We know that the acceleration for gravity, -10 meters per second. And the change in velocity, let's say it's just going from the bottom to the top. So that's going to be starting at 40 and ending at 0. 0 minus 40 meters per second divided by the time. You'll find that this time is 4. That's the time just to go up, so the total time is 8. A very quick way to do this, and this only works because we're assuming that gravity is 10 meters per second. A quick mnemonic is to go between these two, there's a factor of 5. So if I want to quickly go from 40 to 8, I can divide by 5. Or if I want to quickly go from 8 to 40, I can multiply by 5. Technically, what you're really doing is dividing by 10 and multiplying by 2, or multiplying by 10 and dividing by 2. But a quick way to go between those is to take this number divided by 5 to get this number. Okay, now that I have the total time that it's going to spend in the air, in the horizontal direction, now I can find the range. X equals v times t. In the horizontal direction, it's going at a constant speed of 40 meters per second. So that one's going to come right here. Wait, isn't it going 40 root 2? Nope, it's going 40 root 2 overall, but in the horizontal direction, we're going to keep them separated. It's just 40 meters per second here. 40 meters per second, I know the time in the air is going to be 8 seconds, so the total range is going to be 320 meters. That's how far it's going to go. This is, of course, assuming no air resistance as well. Let's do another example. Let's have an angle that's not 45 degrees and see how we can do with that one. Let's say walrus comes and kicks the ball along from ground level again. I'm going to scooch my ground level up so we have a little bit more space. There's ground level. there's the ball, and let's say that this time it is at 30 degrees. So there's 30 degrees. And let's make this, how about make it really fast? 60 meters per second is my initial velocity. And once again, I want to find out what's the range. Where is this going to go? So how do we do that? Well, first off, break things into components. We've got this component and we've got that component like that. So I want to find out what's my V0y and what's my V0x. As a quick trig reminder, this is a 30, 60, 90 right triangle. And the ratio of those sides, 30, 60, 90, if this side is x, then this side is 2x, and this side is x times the square root of 3. So x, 2x, and x root 3. Which means if I know this one, I divide it by 2 to get this over here. So this 60 divided by 2 makes this 30 meters per second. And then this one is going to be 30 root 3 meters per second. Vertical direction, figure out the time. My problem is I've got an initial speed of 30 meters per second and I want to find out the total time in the air. 3 seconds up, 3 seconds down, 6 seconds is my total time in the air. Horizontal direction, how far does it go? X equals v times t. Now I take this 30 root 3 right there, 30 root 3 meters per second times 6 seconds, and that gets me 180 root 3 meters. So that's going to be the range right there. So we can also ask other interesting questions. So for example, how high does the ball go? What's its maximum height right here? The maximum height is going to be halfway for its total range in the horizontal direction. It'll reach its maximum height. I can use the vertical direction to figure out maximum height. I can also be given different things. If I'm given the range, I can work backwards to figure out, say, the initial horizontal velocity, work backwards to figure out the initial vertical velocity, or the initial overall velocity, something like that. Remember to keep them separated. That's the whole idea. I want to tell you one last thing is the triangles that we're going to see. We're going to see our isosceles right triangles, which are 45 degrees. That's going to be x, x, and x root 2. The 30, 60, 90 triangles, which I just showed you, 30, 60, 90, x, 2x, and x root 3. And then we're going to have 3, 4, 5 right triangles. And those angles are actually 37, 53, 90. Not exactly. So across from 37, this is going to be 3x, 4x, and 5x. For example, if I gave you that this was an initial velocity of 40 meters per second at an angle of 37 degrees, you know that the vertical component right here is going to be 30 meters per second, and the horizontal component, oh, I totally did that wrong. Oops. Sorry about that. Switch that. 3x, 4x, 5x. Let's make this side 50, and that side 30, and that side 40 meters per second. Okay. Hopefully you watched it long enough to see that that was my mistake. Of course, if you are a trig person and you want to just do any old angle, that you want to look at any angle that's possible, then you're welcome to use some trig, which we may or may not do. So if this side is theta and this side is VO, then your VOY is going to be VO times sine of theta, and your VOX is going to be VO times cosine of theta. So you're welcome to do it that way as well. Okay, good luck. You should have enough information now to do your worksheet problems. Bye.